if you know, there's a good way to
visualize. Yeah, you can't get a temporal kind of a view of different warps. It's not at that granularity at least.
Right.
Yeah.
Okay. Thank you.
Yeah. Okay. All right.
Thank you. So up next, we have Chris Lattner. I'm sure everyone in the room has used his code, whether it be LLVM or Swift at some point. Truly storied hacker. So let's hear it for Chris. Woo!
Better at compilers than AV. One second, let me just get on the Wi-Fi real quick. Okay, good. They just load some images.
Attention is all you need.
Yeah. Oh, that's looking a lot better. Needing to be connected. It should be a little bit less than 5 minutes. Change resolutions 50 times. All right. So, hi everyone. I'm here to talk about what we're up to at Modular. So this is kind of a personal quest, a journey that we're going through. It's pretty exciting. I hope it's interesting, and it touches a lot on GPU programming, among other things. So one of the things that I was lucky to be around was Dave Patterson and this time of this rise of heterogeneous compute. And I've seen a lot of computers be created from CPUs up through all these things. I work on TPUs at Google. And one of the things that he talked about is that there's this amazing golden age of new computer architecture. You look at what's happening with GPUs, TPUs, all this stuff. Dave he gave this talk at his Turning a Word lecture, and it was really impressive. Now the problem with this is that there's no software for this, right? There's all this hardware out there, and everybody's still struggling. And so when I was at Google, I was leading a bunch of the AI infra stuff that I saw, and we had TensorFlow with graphs. We were working with CUDA, of course. TPUs had to create their own thing called XLA, and mobile had a completely different stack. We also had like 7 other chips, right? And one of the things I learned from this is that there's like all these different stacks. Everybody's reinventing the same things, and so one of the projects that came out of this was this MLIR compiler thing that's now public, part of LLVM. Lots of people use. I got fed up with Google. I didn't get along with the culture, honestly, and I jumped to a startup company. And a startup company building hardware called Sci-Fi. They're building very fancy RISC-V stuff. Super cool. Check it out if you're looking for CPU IP. We built an AI product, and the AI product, then you say, okay, cool. We know how to lay down a systolic array. We know how to make all this stuff. We know memory fabrics. Awesome. Where's the software? So again, ran straight into the face of, we have all this ability to build hardware, but where is the software? And one of the problems is that there is software out there, but it was never designed to be general. It's always designed for somebody else's thing, so you're looking to repurpose something, particularly if you're a startup, right? And so, being the smart person that I am, cool, what do I do about this? Well, I decided to go give a talk. And so I gave this talk, kind of a dual to Dave's talk, talking about, it's actually a golden age of compilers, and what we need is we need all the software, and people should stop reinventing stuff, and they should standardize things, and guess how well it worked? Not at all, it turns out. And why is this? Well, almost nobody can even build one of these things for one chip, right? The big companies are the ones that are building all this stuff. They want to lock you into their chip, or their cloud, or their whatever. Right? I love all the MLR people, and all the compiler people, and all this stuff, but it's super fragmented, super weird, super academic. There's a lot of motion, but no progress. And also, this is just like outrageously expensive to solve as a problem. So I got very annoyed by this, and at the right time, we decided let's actually solve this, and that's what really Modular is about. I'm going to tell you a little bit about what we're doing with this problem. So when we started the company, we said, okay, this is outrageously expensive. This is a big problem. And so this is a slide we use internally, and so we said, let's take this in a 3-step process. So the first thing we did was we said, let's go solve CPUs. Well, why? Well, you need a CPU to feed a GPU. CPUs are more general. CPUs are actually more difficult in some ways than a GPU. Next, go solve GPUs. Obviously, this is a huge problem. Even 2.5 years ago, pre-ChatGPT, GPUs were the thing, right? This is obvious. But we want to make sure to tackle this in the right way. And then once you get these abstractions scaled into here, you can all go tackle all the fun, other cool stuff that's happening in the universe and edge and like all that kind of stuff. And so one of the things that's really important about our approach here is that we want to make sure that we're actually validating what we do. And so I'll talk about performance and other things like this. So let me tell you how stupid this idea was. Okay. And so what are we actually trying to do here? Right. We want to beat vendor performance on their own chips. These guys have been at it a long time. They have trillions of dollars, at least in market cap. Right. We want to beat usability of all the existing stuff. Right. We want all the research quality stuff that the world has been building on top of to graduate and grow up, because everybody wants to build on top of AI and they don't want to always have to deal with it themselves. We want to unlock research. We want, like, for example, Tree's amazing talk, we want all that stuff to go faster, and we want generality so there can be innovation at the hardware level. And so if you look at why this is hard, just on CPUs, well, just within CPUs, you have massive architectural differences across the macro architecture. Even if you pick Intel, you have now massive numbers of different instruction sets, and AMD just added bfloat 16 fancy things, and like you have all this like diversity that you have to deal with. You can't scale. Like you can't just write all the kernels. These are also complicated. You've got SIMD, you've got NUMA architectures, you've got distributed machines, of course. You've got tensor cores, what they call them AMX instructions, and things like this. And this is often like a super mature problem space. People have been working on this for a long time. So let's take a new approach. So one of the first things we did was we built this completely new programming language called Modular. This is very confusing to people. I think a lot of people don't understand why you would be insane enough to build a programming language. But let's start with what it is. Well, Mojo is a completely new programming language. So this is a new compiler built on MLR, all kinds of fancy technology underneath it, that looks like Python. And so it's a member of the Python family. But it's a systems programming language. This is not the Python that you know. And the systems programming language is really important. Now, making a language successful, you have to build all the tools, and so we've done that. It's freely available. You can go download it. We're open sourcing under Apache license. We have something like 50 patches a month coming in, and we're kind of getting crushed under the interest. But it's all very cool, even just for CPUs. We have a nice community. You can join us on Discord. But what is Mojo? What is this actually about? What we're doing is we're taking the things that I love about Python. What that is it's the developers, the accessibility, the number of people who know Python. And we're taking the ecosystem of code that already exists, which is all the packages. What we're not taking is we're not taking its implementation. And so what we did is we brought in a whole bunch of next generation programming language, compiler, and other stuff into this, and we're bringing that together. And so what this means is that while it looks like Python, please forget everything that you know about our friend the state. So is it fast? Yes, it's fast. It's depending on what you're doing, it's like 1,000 times faster than Python, which is cool. We work back from the speed of light of the hardware. We do not work forward from the speed of whatever Python is and try to make Python better. And so something that's very controversial but also true is that we're faster than languages like Rust and C++, because we built an entirely new compiler stack that's not the 15-year-old legacy thing that Rust is building on top of. We also learned a lot from all this kind of stuff. And so this, for example, is just one simple example, is just a classical tokenization algorithm. The thing that's cool about it is you can just write for loops in normal code and it goes fast, right? And this is actually pretty profound when you're looking at ML systems that are fractured between often C++, Rust, CUDA, and and Python, and like all this stuff together. Now, we'll get to AI more in a second, but if you look at AI models, you can download today. We're something like 6x faster than Llama.cpp at Int4 on Intel machines, which is pretty cool. And what that is, that's a combination of not just having a fast programming language, but a lot of the technology we'll be talking about in a second. And so if you want to try this out, you can go get this. This is actually a pretty big deal because I think Lambda CVP is what really invented M4 and 6 and stuff like this. So I want to talk about GPUs now. So unfortunately, our GPU support's not quite done yet. It's coming out soon. I'll talk about that in more detail, but I'll talk about why our approach is hopefully interesting. Before I do that, let me tell you why it's hard. I think you know a little bit about this. But first of all, from our perspective and from the system's perspective, you have to have things like offload. Like you have a host and an accelerator talking to each other. You have split compilation. We want one program that can talk to all the different parts of this. Now for us, that means split compilation across multiple architectures, which is exciting. You also have even more complexity. You have the asynchrony that Tree was talking about. You have tensor cores. A lot of this is actually similar in spirit to what CPUs have these days too. But also, it's more than just a kernel. Like AI today is like page attention, right? It's these LLM optimizations, the higher level systems. And this is where a lot of the performance unlock comes from. And so, you have to get the kernels right, that's right, but that's not just where the performance comes from, it's a whole system architecture approach. And so what we wanted to do is we want to do all this while maintaining the same programming model and make sure it's consistent across CPUs, because these machines we program are heterogeneous, they're not just GPUs or CPUs. So what we did about this was we created an entirely new AI framework. It's called Max. It's focused on inference. Yes, it talks to PyTorch as well, and so you can do training with PyTorch and things like this. We're building into this. I'm not going to spend a whole lot of time talking about this. I'm going to talk about GPU stuff instead. But what you need to know about Max is as a framework, it brings together all of these best-in-class algorithms, things like XLA or TVM or ONNX Runtime or CUDA or TensorRT-LLM, like all of these systems, it brings it together into a next-generation system that we've built using the experience that we all gained building the first generation, which is kind of damaged and flawed in various ways. So I won't be talking too much to compiler here. And so what we did is we said, okay, well, let's actually go and build a full stack replacement for the modern GPU stack. So this isn't just a replacement for CUDA, C++, or something like this. This is a full stack replacement including driver, programming language, kernels, LLM optimization, and serving to provide the full stack that is now portable and can be used on multiple different architectures. And so one of the things that's cool about the stack is it's very consistent for CPU and GPU, which means that you can get actually I think perhaps the world's first real unified local to cloud development kind of environment, which is really, really quite nice. So let me show you some code. Let's start with the basic stuff. If you write CUDA, then you've seen thread IDs and things like this. One of the nice things about this is in Mojo, you can just go nuts and use everything you already know, but now you're in Python land. It's Mojo land, but it looks like Python. And so this works exactly the same way as CUDA does. Compiles to PTX. You get all of the fancy, powerful features that you'd like to use. The thing that's really cool about Mojo versus CUDA C++ is, first of all, it's not C++, which is kind of cool. It's easy to learn. But the other thing is that how should I say this? Can I be mean? SD tuple sucks. There's so much about C++ and STL and templates and compile time and this whole nightmare that we've been living with C++, it's just driving us freaking nuts. And so what Mojo does is it brings a super powerful net programming system, if you're familiar, derived from like Zig and other more recent languages into this world, which enables building these abstractions and doing high level programming. But the basics looks the same. You can do everything you've done before, and it's all consistent. Now, when you bring in this power of Mojo, and what does it enable you to do? Well, one of the things you can do is you can build fancy abstractions on top. So one of the things that we're inspired by is, for example, the Triton language community has done some cool stuff for bringing tile-based programming into the world, and Cutlass, and lots of other people have done this. And so what we did is we said, okay, well, let's actually build this in a Mojo, not as a compiler, but let's just build a library. And so what we allow you to do is do fully async tile-based programming. Yes, it's forced dynamic shapes. Yes, it's forced TMAs. Yes, it's forced tensor cores, of course. Like, that's all kind of table stakes these days. But the cool thing about this is it's simple, predictable, and it gives you the full power of the machine. And so if you're curious how you can get simple predictability and full power of the machine, it's very compilery, and so we gave a talk at the LVM meeting in the fall, and you can find out more about that, how that kind of stuff works. But one of the things that's very important about our approach here is we're not trying to put all the magic in the compiler and take it away from kernel authors. What we're trying to do is we're trying to make it so that smart, advanced developers can go use the basic features to build, for example, asynchronous memory pipeline fancy thingies that I conceptually understand, but I'm definitely not an expert at, by the way. And then build these things into libraries and build abstractions into them, and then reuse them. And this is how software has generally worked and scaled, and so what we're doing is we're learning from traditional software and pulling it forward. And then, yes, giving you fancy integration with the graph compiler and staticization and autofusion and all this kind of stuff that then makes it so that you get a richer programming model. One of the cool things about our stack with Max is that being able to write a custom kernel is very important, but being able to not have to write a custom kernel is actually pretty cool. And so we provide a very simple graph-based programming model. When combined with our auto-fusing fancy compiler, it means that you just get fused kernels. And you're not going to get a tree quality fused kernel out of this probably, right? But one of the things that's really nice about this is that this thing, which you can put in the category of like XLA or something like that if you're familiar with this, makes it so you can just write code that looks far more like PyTorch, and you just get pretty decent quality fused kernels out of the box. And what we've seen is that in many cases, this beats like the hand-fused kernels you get out of QDNN and things like this. And so the combination of a few very fancy kernels combined with a graph compiler gives you a lot of power. And the nice thing about this is that you can think about things from a math perspective instead of having to think about all the different implementation details of this. As I mentioned before, we have a driver, and so we're not just talking about programming language stuff. We actually, to talk to a modern GPU system, you often have many GPUs. Some people want to control things at a very low level, and I believe in giving people full control, and so you can go nuts, and you can create different devices, and you can select kernels, you can copy memory, do all this stuff. One of the nice things about it is that it's architecture agnostic, and so it's very funny, in Python you can open your CPU and submit high performance kernels to your CPU, and now you can offload to the same machine you're on until it works. This is even more powerful in the future when we bring in distributed support, because you want to be able to open up a GPU on a different device or on a different machine and things like this. So there's nothing like rocket science about this. It's just really nice, it's easy to use, and it's familiar, but it's also portable as well. One of the things that's also really important about getting performance is tools. And so a lot of achieved performance is being able to use things like profilers. A lot of achieved correctness is debuggers. And so Mojo as like a full tool chain and actual language, one of the opportunities that affords us is we can have like direct integration with CUDA GDB, with Insight Profiler, all this kind of stuff. It all works exactly as you'd expect, and it's completely native. And so this is really important for our team to be able to get high performance on these crazy modern architectures we're all dealing with. So anyway, so what I told you is that we're building a whole bunch of crazy stuff. This is actually really hard, the scope and scale of what we're doing. And so you might ask how much performance you have to give up to be able to get better usability. And so we haven't launched, and we're not ready to talk about everything, but we can show you some examples. We did a study of our matrix multiplication written in Mojo, and by the way, all of our kernels were written in Mojo. We compared against one vendor, which is pretty popular around here, called NVIDIA. Their market cap is a few $1 trillion more than ours, by the way. But one of the cool things is that we're able to already beat QDNN and Cutlass by a little bit. And that's actually pretty profound, because this is head-to-head drag racing on Tensor Core. Like, this happens to be on A100, but this is just like drag racing on fully dynamic, doing the exact same thing. This is not staticizing or cheating or other things like this. This is also not bringing in the advantages of kernel fusion and all the other stuff we're talking about. So we'll be talking a lot more about performance later, but it's pretty cool. And TLDR, you don't have to give up performance. In fact, you can get better performance because you can understand what the code does. So let me tell you an open secret about all this stuff. So we're an AI company, Modular AI, but none of this really has anything to do with AI, really. This is all about accelerated compute, right? And so the thing that I think about, and the real motivation coming back to the beginning, is that hardware is changing, right? You think about programming today's systems and what a pain in the butt it is. Think about what we'll be in 5 years. There's going to be more hardware, more diversity, more specialization, more craziness, more fancy algorithms burned in silicon, because fundamentally silicon is two-dimensional, and so you're going to get more things like tensor cores that are going to be specialized to the application. So I'll wrap things up. The whole point here is we want to give you superpowers, right? So we are about enabling programmers, we're about giving you cool tools, we don't want to put all the fancy stuff into a compiler, we want to give you the power of fancy compiler tech. If you go check out our webpage now, you can download Max and Mojo and have a lot of fun. There's a lot of LLM things, you can play with PyTorch stuff. The open source community is building things like GUI libraries and serving frameworks and all kinds of stuff because Mojo is very horizontal and very nice. We have nightly builds you can check out as well. We're launching our NVIDIA Sport this fall. I'm very, very, very excited about this. I know a lot of other people are as well. Secret for y'all, we're going to be doing a marketing launch late this fall, but this will all be available in our nightlies in like a month-ish. And so we're not going to make a lot of noise about that, but if you're curious about that, please join our Discord. How much does it cost? By the way, it's free. This is not a try to lock you into a thing. Our whole business model is around enterprise support, about building managed services and things like this, and so we do want to let you get a license if you want to go build a managed service and compete with us, but if you're a researcher, if you're playing around, if you're building your own stuff, if you're a massive AI research company or whatever, like, go have fun, that's cool. So imagine a world where you can have innovation unlocked in hardware. We don't have to force people to learn Python, C++, CUDA, Rust, like all these things. We can have unification. We can expand and close this. We can close this gap between research and production. We can have more AI in our lives. If you're interested, please check us out. We're on the web. Also, we're hiring a ton of systems people, and if you're interested in high-performance GPUs and end-to-end performance and LLM optimizations, any of this kind of stuff, then it's a really exciting time. So that's it.
Question?
Is there support for Jupyter notebooks?
Yeah, we totally support Jupyter notebooks, for sure.
With compilation or interpreted?
That's a complicated question because we use JIT compilers. Yeah, we have a lot of compiler stuff going on. I didn't even touch into it, but yeah.
So in the example that you showed, there was like thread-id.x, block-id.x. So you mentioned that there's no difference between the CPU programming and GPU programming, but what if you like run the same program in CPU?
Yeah.
What would those?
Great question. We're not trying to make different architectures be the same. We're trying to remove unnecessary differences. And so if you have a tensor core, like you need to be able to reason about a tensor core. Like you need to be able to reason about the architecture. But on the other hand, if you need to overload an operator, you don't have to learn a new way to overload an operator. Just use dunderad. And so what we're doing is we're like the cloud-based programming model works on CPUs and GPUs, but the architectural differences are things that kernel experts need to own. And so we're not trying to erase that.
So, you know, there's like that XKCD about how like, oh, there's too many standards. Like, we need to create a standard that like unifies everything, and then it's like there's another standard. I'm curious, like, what design principles you're trying to put into this effort to like prevent that,
Yeah.
or just how you're thinking of it, given you've literally built like a lot of the ecosystem already.
Yeah. So I don't know what other standards you're referring to. You're referring to PyTorch, Sickle, like One API.
Yeah, I guess I look at the Max, like the framework where it's like we're building our whole stack like all the way down, and it's like how do you prevent it from being like another stack on top of it? Like what I'm curious, like what if there's a takeaway principle that you are like anchoring to when you're building all this out.
Excellent question. So I'll tell you what we're doing. I can't tell you that we're right. What we're doing is we're learning from the past. So take One API or Sickle or things like this. They're all based on OpenCL that like Raja and I and other people worked on in like 2007. Right? The world has changed fundamentally. Like you need tensor core first programming models and things like this. And so learning from all that kind of stuff and being able to move forward and reinvent what makes sense, I think is very important. If you're looking at PyTorch, well, PyTorch is struggling with GenAI. GenAI fundamentally changed the game because it's not about a graph anymore, right? It's about fancy optimizations where you're utilizing many GPUs. Like you're like a lot of the things that made sense back in the TensorFlow days or things like this, they don't translate forwarding, and so a lot of the assumptions that these systems were built on top of break.
Right.
Now, will this thing be a mess like the last ones? Well, probably.
But there's
a
like a
little
set
bit.
of assumptions that you're encoding in it of like.
Yeah, what we're doing is we're just learning from this. Like I mean, TensorFlow, PyTorch, JAX all date back to 2015, right? 2016, and so a lot has changed in the industry since then. Yeah, Fish.
I don't remember if I've asked you before, but there is like the scalable vector extensions, which is the kind of CMD instructions of variable length. Do you already support those within Mojo, and what's your way of thinking about them?
Yeah, so when I was at Sci5 doing RISC-V, they
Mhm.
also have their thing like SVE, but for RISC-V. There are good things about it, but massively overplayed in terms of hardware abstraction.
Mm-hmm.
So for those who don't know what variable length vectors are, the idea is that you could write, for example, a dot product and write it in a generic way so that it can adapt to future generations of hardware that change the architected vector length. That's dumb, because when you start doing, for example, in MATML, you have to know how big your cache is.
Mm-hmm.
Right, and so the good thing about those ISA features is they make so you don't have to re-encode your entire instruction set every time you want to change the vector length. But you still need fancy compilers and architectures and kernels that can make you adapt when all the parameters of your architecture change. And so what we do is we say, okay, yes, you can access that, and you can talk to anything that LLVM or MLR, and like our stack can talk to anything in principle. We haven't implemented everything, of course. But it doesn't solve you from having to solve these. It doesn't prevent you from having to solve these problems. Now, I didn't talk about it in Mojo, but in Mojo, it has this very fancy parametric metaprogramming system, and so by default, it encourages you to write generic algorithms. One trivial example, which I know you'll like, is that we don't have scalar and SIMD types. Scalars are just a SIMD of 1. Right, and so if you're writing sine and cosine, of course you write it to be generic on your vector length, right? And things like this. And so there's a lot of very simple things like that that go a long way.
Very cool.
How does it work on Apple devices that use Metal? And do you see yourself as competitive with that? I guess sort of more global question. For all of the existing CUDA competitors, why has CUDA managed to beat them out for the most part?
Okay, so let's separate these questions.
Two
So,
different questions.
yeah, so we are coming out of CPU land, we're doing NVIDIA. And NVIDIA is really important to us, they're a great partner, and they have really cool stuff going on, of course. So we haven't done Apple GPUs.
I see.
We've talked about it. His team says it'll take 3 weeks to do or something. But we have not done that. Oh yeah, Mustafa leads the GPU group and a bunch of other stuff.
I see.
Yes, and so he's also a lead CUDA hacker. He led CUDANN back in the day and
3 weeks to
things of that. So my problem is I have to keep people focused. And building the world's best GPU programming model that exceeds what people are used to with CUDA is really hard. Okay, and so I want to make sure that we do something that's really meaningful and it's a contribution to people that are actually programming GPUs, not being another thing that's like a demo that only works in special case. And I like building production stuff, and so we'll expand out when it makes sense to do that. And Apple GPUs are very interesting, most notably because local to cloud, and lots of people are using Apple laptops, and so I really love that community for lots of reasons. And so I suspect we'll do it at some point, but we haven't done that yet.
And the second question.
Oh yeah, sorry, what was the second
So
one?
why has CUDA been so reliably dominant, and how do you frame?
The way I would say that is, so I think there's many factors that go into CUDA being dominant or successful. One of which is that it was ahead of its time and executed well. The other is they kept compatibility. And a lot of the other people, every 3 or 4 years, they'd lose focus and try to do a new thing, and they would just fragment their internal stack, and they would, I'm not going to name names, you know all the other names, right? But they just turned into a software nightmare, even within their own walls. And trying to unify FPGA programming into GPU programming is
I see.
a little bit of a fool's errand.
So we shouldn't expect Mojo to ever get compatibility.
Well, so that's a little bit of a different thing. I was talking about hardware compatibility, right? And so other people, for example, had different software lines on, for example, laptops versus data center and things like this. So, but again, there's a lot that goes into that. CUDA is also really well executed. Also, the hardware is really good. Right? I mean, there's many different factors that go into success.
Last question.
Yeah.
Yeah, similar along the lines of the question about the thread IDX on the CPU. Could you compile the SIMT programming model to SIMD on a CPU? So could you program a CPU using the same kind of model?
Let's talk later.
All right.
Don't have anything to say about that right now.